I'm always on the lookout for demonstratable processes that I can have in the classroom. The smaller the better, without a lot of heavy manufacturing. In other words, I don't want to develop dies and molds. This is a classroom idea. It's an operational garage door to use in the classroom. And this is a project that I did. Everybody's familiar with this type of garage door. The primary actuator is a reversible motor that pulls the garage door up into a track horizontal, and then when you send the garage door down, it goes back down the track in segments, curving around through the track back down to the floor. Now, inside of that housing up there with the reversible electric motor are limit switches that are actuated when the door is all the way up to stop the motor so it doesn't pull any further up, and when it goes all the way down, as soon as it gets down, it releases another limit switch or trips another limit switch to say that it's all the way down. In addition to a reversible motor, AC motor, up and down extreme limit switch for travel, you also have a safety photo eye across the bottom of the door in case something's setting in the way of the door. The door will not go down or continue going down if it's already going down if that photo eye is blocked. But blocking the photo eye will not prevent the door from going up. Keeping in mind that we want this to be easy to build. So I did not build one that had a segmented door that rolled up into a track. All that manufacturing or all of that construction is just a waste of time. And there's two ways that I could have done the garage door. This is the type of door that we're going to build, and it just goes straight up into vertical tracks. You could also build this laying down, meaning it's like a garage door apparatus, but it's laying flat. That way you're not taking up a lot of space. I decided to build mine vertical just like this to make it a little bit more realistic. So let's take a look at it. First, let's play a video of it operating, and then we'll discuss how it is built. The actuator, or the motor and the mechanism, is the single greatest challenge to this project. Trying to build a segmented door with tracks that go from vertical to horizontal like a regular is out of the question. I had to come up with something that would move the door up and down that wasn't real large, wasn't very expensive, still gave us a large enough door. This actuator actually has a 5-inch stroke, and it was the largest stroke I could find in something this small. And it's a DC motor. It's a non-reversing motor. You can reverse it by polarity, but not by phase. It's not an AC motor. And this particular actuator, linear actuator, was the third or fourth one that I tried. Some of them I sent back just as soon as I put my hands on them. I knew they weren't right. And they were hard to kind of get out of the way, meaning that they were just too large for a mechanism this small. It would have worked okay, but it would have looked really bad. We started out with the actuator, and this is the limiting factor for this project, is something that can raise the door up and down that's not real big and that can be reversed. Use this particular actuator, and this is, I purchased it off of Amazon for, it might have been less than $28 when I bought it, but right now they're $28. And you can see in the description the stroke that I picked was the largest one. I wanted the largest stroke I could get. If it had been 6 inches, I'd have bought a 6-inch. The stroke of this actuator determines the height of the door. We want to be able to raise the door all the way up and, basically clear the top of the door somewhat, and then all the way down. The height of the door, or the opening, is limited by this actuator. Everything in this design hinged around the extended and retracted length of this actuator. In the photograph, you can see that it's fully extended to 5 inches, and if you look at the total length, which is 10 inches, that determined the height of the mechanism, or the height of the garage door demo. And I only built one of these. There were several cuts that I made, several things that I did that to do it over again, I would make it a little longer, a little shorter, just so it's a little bit more tidy. Everything was determined from the retracted and extended length of this actuator. That would be the height of the wall, the height of the opening for the door, and the height of the door. Now the width is a different story. The width could be anything that looks reasonable. In this case, this is the aspect ratio for the door, like a single car garage door or a loading dock door in a warehouse. So the force that this motor can produce, 1/8 inch, weighed practically nothing at all. So I knew that this would work, and it was the smallest that I was going to be able to find that would be unobtrusive in appearance somewhat. I mean, it doesn't really look like a garage door motor and chain mechanism, but I knew it would work. The challenge then would be to make it behave like a reversible AC motor, because when you're going to do the garage door project in the lab manual, you are energizing a forward and reverse starter. You are treating it most likely as a 3-phase motor, and you've got reversing starters on it, which means you have a separate output from the PLC to tell it to go up and a separate one to tell it to go down. And there are several ways you can do this with relays. It's going to take at least 2 relays no matter how you do it. At a minimum, one relay turns the power on and off, and the other selects the direction. So you could take a double pole, double throw, and flip the polarity to the motor based on whether the coil was energized or de-energized, and then your primary relay just uses a normally open contact. When you energize the relay, it closes and it feeds the 12 volts DC into the second relay that determines whether the motor's going to go forward or reverse, up and down. So I wanted it to behave like it would if it was a reversing starter. Separate signal for up and a separate signal for down. Not some combination of relays that gave you the same effect. That would be the easy way to do it, but I wanted it to behave like a reversing AC motor. So that actually took 2 4-pole relays. And this is the circuit. So if you look there, we've got up relay and down relay. Now you may be thinking, well, I don't see 4 poles there. Well, you can't use the common of one pole and then use both the normally closed and the normally open. It just does not work out, which means that you have to use one contact from each of the 4 poles. So for up, I've got 2 normally closed. Now also keep in mind that because this is for classroom, I want to avoid the possibility of the students shorting the system. Now, they're going to wire this up, maybe not the entire thing, but they're at least going to wire the outputs and inputs to the PLC. And if they were going to make other connections, it would be easy to short the power supply. So in this scheme of things, if I tell it to go up, then the top 2 normally closed contacts are going to open. And there's no way that negative is going to go to the bottom of the motor and positive to the top. Instead, if you look down at the other green up contacts that are normally open, it's going to feed the positive to the negative side and the negative to the positive side, and then vice versa for reversing. So if you energize both relays at the same time, nothing happens, because you've basically opened up all the normally closed contacts you see there to the left. So both of the up normally closed and both the down normally closed, they would all be open. There'd be no path for conduction. Whereas if you didn't put in that kind of an interlock and they accidentally energize both relays at the same time, they could actually, well, they'd probably just blow a fuse if you've put a fuse in your demo device. So I wanted as much as I could get out of this, so this is what I did, and this is the circuit. So the 4-pole relays that I decided on using, I got from DigiKey for a pair of them for about $26, which is not a bad price. And I actually prefer this type of mount or socket because of the spring clamp push-in connectors, and there's 2 spring clamps for each terminal. Now the numbering on their socket, although A1 and A2 is the same as on other relays, the rest of the numbers are not. They're different, so you got to pay real close attention to what you're doing. The other thing I liked was that all of the relay contacts, all the terminals were on one side. And then the other side has A1 and A2 to power the coil. But the connecting up the interconnection between the up relay and the down relay, the interlocks, was much easier to do with 2 of these side by side. Here you see the 3 outputs coming from the PLC, up, down, and the garage light. Part of this lab project in the manual is that you have an overhead light in the garage that comes on anytime anything is disturbed and stays on for some set length of time after the last disturbance. And I mean by disturbance, touching any push buttons, tripping any safety photo eyes, energizing any motors, etc. So by habit, because Rockwell Allen Bradley has always used green for output and blue for input on their modules, I tend to kind of stick to that, just a habit. So you see I have 2 outputs, one each going to the up and the down motor. Now 2 outputs, one for the up, one for the down. The third output is for the garage light. So you see it goes to a green terminal block, and then a red wire comes out and goes up to a LED panel indicator that's just hanging loose above the top of the garage door. For inputs, we have 2 limit switches, and we have a safety photo eye, just like you would have on a real garage door. And the limit switches that I used, you could buy a handful of them for $8 on Amazon. And there are smaller ones, but they're more difficult to mount. So this became an issue of figuring out some way to mount it and get it in the proper location to be actuated by the door going up and down and not being too big. So this turned out to be kind of the optimum size. It's got 2 holes, one in each corner, as you can see there in the image, and you can use wood screws or pointed screws, even bolts if you want to drill a hole in the plastic to mount them. It is kind of tricky mounting them because to make them adjustable adds another degree. And then the third input was the photo eye at the bottom of the door. I used a used Keyence sensor amplifier. There's one that I just captured off of eBay today. $23 our best offer, and it's got, you want to make sure that the cord on it is long enough to reach, and you can see in my photo there of the actual installation, you can see the Keyence amplifier, and then right on the other side of the 2 relays, the first blue connector has the black wire from the Keyence amplifier connected into it. And that's going, this is an input, digital input going back to the PLC. And then the actual fiber is on top there, and there's one for $20. I didn't pay that much. I think I got two of them for $24 or something, two pairs. And you can see that one is a transmitter and one's a receiver. They're very small, and they have two mounting holes. Now, I will tell you this, it was a real challenge getting them mounted. And you can't see it from the picture, but the actual fiber turns 90 degrees right near the bottom edge of that little metal bracket. So it is right down on the floor going in the garage door, just like it would be at home. Typically they're mounted 6 or so inches off the floor. Whereas the DC linear actuator was the starting point, because its retracted and extended length determined the primary vertical dimensions of this. Once that was established, then you needed the vertical extrusions, with the T-slots. And, you can buy a handful of these on Amazon. I see here $17, and they are 15.8 inches, which was plenty long enough. This is the actual, after you get the actuator, and that was, the length and everything, you knew what you had to have for height. The next thing was to mount these two extrusions vertically off of the base. Now the base, I always use 1/4 inch ABS. I buy it off of eBay. It's not very expensive. I cut it on a table saw, and then I cut two thin strips the same length, and I use ABS glue to glue them on the bottom edge on each side. That gives you a little bit of a standoff, so the nylock lock nuts on the bottom don't rub on your table surface. I estimated the width at about 6 inches, and I drilled 2 holes that will allow me to mount bolts up through the bottom of the base into the hole on the extrusion. Now you can order these pre-cut and pre-tapped from Misumi, M-I-S-U-M-A. These, I bought these off of Amazon, and then I use a tap out of my tap set to tap the holes that are on the bottom. Now the thread that you use is up to you, whether you use metric or SAE, but there is a limit to how much you can tap into these holes. So once I had them tapped, then I took and ran a bolt up through the bottom of the base into the threaded end of each of those vertical extrusions and tighten them down. Now I have L brackets on there. That is not necessary. I just added that to give me a little insurance on, that they were lined up properly. The next step, after you have the extrusions mounted, is to determine the width of your garage door. Because remember, the garage door has to slide down in these slots. Now, 1/4 inch ABS will slide down through these slots. I use 1/8 inch because that's what I had on hand, and it kind of wobbles a little bit, interacting with the springs on the limit switches, which gives it kind of an odd look when you're watching the video. The front of this, you're going to mount a plate up at the top of this structure that will give it its rigidity. The inside of the garage and the outside of the garage, I didn't pay particular attention to the aesthetics. I did use a piece of white ABS as the base plate because that's what I had. And then I didn't like the way the garage door looked on the white floor, so to speak, so I painted that end of it gray, spray painted it, and the door is white. So it looks a little bit better than if it's just all black, because if it's all black, it's really hard to see. There was an upper piece, you can see, of ABS that is bolted to those two extrusions. Now remember that all these elements are bolted to the extrusion with T-nuts that slide in, and then as you tighten down the screw or the bolt, it rotates the nut underneath the inside edges of the T-slot and locks it for the holes that they line up real well with the vertical parallel of those two extrusions. In other words, when you put this piece on, this upper piece, you don't want it binding at the top or the bottom. In other words, you don't want space between the two T-slots, between the two vertical extrusions, narrower at the top than at the bottom, or vice versa. So you need to pay particular attention. Now, you could slide a spacer the full length of these two extrusions in the T-slot to make sure that they don't get squeezed together the top or the bottom. And you also see up at the top there's a screw. That is what holds the top of the actuator on the inside, and then you see on the garage door down at the bottom, you see another screw. And if you compare that to the image on the left with this one on the right, you can see the correlation. And then there's two tie wraps that are used to tie wrap wires and the fiber cable from the fiber optics. And again, the actuator, if you use the one that I show you here, that's 10 inches fully extended and 5-inch stroke, then from that you can determine your distance or length of the extrusion and how much of a garage door. Now, so you might make yours wider. Okay, I'm not giving you exact dimensions for anything other than I'm saying exactly what the actuator was. All the rest of it, that's up to you. This was as small as I could make it and still be able to do it with simple components. Mounts to the front plate, I'm using a long bolt, and I have 3 nuts on it. One nut holds the bolt tight to the front of the garage, and then I have another nut that spaces the actuator out away from that plate so it moves freely. And you can see my garage light, that's just a LED. I didn't want to spend the money on a white one. I already had a yellow one or an amber one, so I just used that. If you decide you want to use L brackets, and you can go to Masumi, go to their website, type in angle brackets, and you'll come to the category. You can go through and pick out something that you like. They're not very expensive. Any L bracket would do. These just look a little nicer because they're a cut extrusion as opposed to like just a flat steel L bracket that looks kind of chintzy. Also, for my positive and negative bus, I use these terminals that I also buy on Amazon, and you can see they're $29, and you get a handful of them. I don't see the number there, but there's a bunch of them, like, I don't know, 32 of them maybe. And then you get some end anchors, and you get some side covers and some jumpers that you can cut to the count that you want. And you see 5 of these connector blocks over there on the left end by the fuse block. Now that fuse block, they're also extremely inexpensive on Amazon or eBay, and that's the 12 volts DC. So remember, my PLC is 24 volts DC, but the actuator, that linear actuator, I could not find any 24 volt ones that were anywhere near that small. So I had to use a 12 volt. So I have a separate 12 volt power adapter that comes in through that terminal block on the left side of the DIN rail down there. I have a 2 amp fuse in it. I use that for the switch. And by the way, you see that LED kind of hanging out in the breeze? That's so I know that I have power there for the motor, because the power adapter doesn't have a light on it. And at one point I had a jack that I had to repair, but in the meantime I just grabbed this out of my stash of maybe I'll use it someday stuff and just plugged it in there. That way if the LED's lit, I know I've got 12 volts DC to power my garage door. Students love this kind of stuff. I didn't do a really bang up job on this. I wanted to make it functional and not too ugly, so the wiring's just a little imperfect. The dimensions aren't exactly what would have been the best, but I wasn't about to rebuild this just to make it look slightly better. This is very important information. I'm sure that you grasp that the height of this wall has to accommodate the full extended length of your actuator, and the height of the door, or the dimensions of the door height-wise, have to match the stroke of this actuator. Another thing you have to take into consideration is the limits of this actuator. If you're applying voltage to the little DC motor in this actuator and it comes up against a hard stop and the motor is still energized, you're going to stall it and you could burn it out. DC motors basically become a dead short if they can't rotate and produce any counter EMF. So you have to consider all the dynamics involved here. So we're going to go through that here real quick. The first one is when you energize one of these relays, there's a little LED that lights up there. Now also notice that there's a little turquoise lever that if this relay is not energized, you can rotate that upwards, upwards and to the left, and it will close those contacts. In other words, it will open the normally closed and close the normally open. Of course, you don't want to do this unless you are really paying attention to what you're doing. But that relay will energize, that little rectangular under 24 volts, that's an LED, that'll light up, and when that lights up, you should be going up. In other words, it should apply the polarity to the DC motor in that linear actuator to drive it up. And the goal is, as it's going up, we want to hit that limit switch. So that limit switch has to be adjusted in a position where the door stops going up before you hit the internal limit switch in the actuator. So this actuator has two limit switches built in, fully retracted and fully extended. You don't want to use those. That's not the goal here, is to get the garage door to go up and down. The goal here is to write a program to control a garage door, but have the up and the down limits be controlled by the limit switches, external, the ones that you wire into inputs on your PLC that tell you that it's up, so it turns the motor off. And the way you can tell that it's hit its internal limits, if that relay, that with the arrow pointing to it, that's the up relay. If that LED is on and it stopped retracting, then it hit the internal limit and did not hit the limit switch that you installed and adjusted to hit. One thing I will point out is, it's hard to see, but the down limit switch, which is tripped right now, is tripped by a little piece of plastic that was glued to the top right corner of that garage door. So as the door's going down, the roller on the limit switch meets that little piece of plastic and it trips the limit switch. So you see there's some things that you're going to have to do here. It's not that critical where you put that little piece of plastic that trips the down limit switch, because the way we design these limit switch brackets is you can loosen that one screw, machine screw, and you can slide it up and down so you can adjust it. It goes all the way up, hits the limit switch, but does not trip the internal limit switch of that actuator. Then when you go down, you energize the other relay and it should trip that limit switch before it gets down to the point where it trips the internal limit switch. I know you want the door to come all the way down to the floor or the concrete pad like on a real garage. However, it would be better if it stopped with a little gap than you to push the garage door all the way down against the we'll call it the apron of the garage or the driveway or the floor of the garage, and then you were still driving that little DC motor trying to push it down further. Now, one thing you can do is the 440 machine screws that mount this actuator. So if you look at the top of the actuator all the way up to the top of the wall, you'll see a screw sticking out there. That is a 440 screw with several nuts on it, but the hole in the top of the wall is larger than a 440 screw, which means there's some slop there. There's some clearance there so the screw can wiggle up and down. Same thing down at the bottom of the garage door. That 440 machine screw has some slop in it, which means that when you're adjusting these limit switches, you have to consider that. And keep in mind, you can operate the up and the down with the turquoise levers on these relays. But if you're building this for your classroom, you need to lock all this down in a way that the students aren't messing with it and potentially burning out that actuator. Now the actuator is only, $25-$30, but still replacing it, undoing the tie wraps, and the length of the red and the black wires from that actuator aren't long enough to come all the way down to those relays, which means that you're going to have to splice in wires if you have to replace the actuator. You don't want to do that. So you want to be very careful. Now, you could limit how far the door goes up and down and not worry about it going all the way down and touching the floor of the garage. So keep all this in mind. Very critical information. I keep adding notes or little tips at the end of this. When it comes to the T-nuts, or some people call them slide nuts, these aren't really slide nuts. They're T-nuts. And if you notice that the width, if you rotate it in the correct position, it will drop right down in the slot from anywhere on that extrusion. So on the right there, you see a machine screw going through a hole in the piece of the black plastic and then going into a slider T-nut that's in the channel. Don't do it that way. Put the bolt in the hole, the nut, the screw in the hole, and then spin the T-nut on it enough so it stays on, and do that with all of your screws and nuts that you're going to attach to the extrusion. So you line them all up and then you let them drop into the slot, and then you hold the piece of ABS firm against the extrusion, and then as you tighten it, as you see in the upper picture, you see it's lined up with the slot, and then as you turn it, it rotates. And if you want to remove the plate or the part, this is the same thing with these switches, the limit switches for the door up and down. So check this stuff out pretty close, and you can find all these T-nuts and hardware on Amazon. Now I think I used M6. I can't remember, but you do a little research, because remember, you may be building a larger one for your classroom than this little thing that I built. This shows some of the construction using ABS and PVC glue. So the glue that you buy at your local hardware store for gluing up PVC, it also says on it ABS glue. So here I've taken 2 pieces of 1/4-inch black ABS, and I applied glue liberally to the edge of the upper piece and then a strip down the middle of the other piece. It doesn't matter if you slop the glue around, it'll harden up. If you just leave it set with gravity, it's going to bond good. I mean, it's going to be hard to break. You could twist it off if you try hard enough. Or once you get it in position, you can use a C-clamp to clamp down on it. I typically use C-clamps to press all ABS components together against the glue. Makes for a better joint with no flex in it. You see the little gap there between the vertical and the horizontal piece. If you look close, you see a little gap. That allows it to rock back and forth, and you could, after a while, bend it and break it off. Also, here's some photos of the fiber ends that attach at the bottom of the garage door. And I have 2 showing the transmitter. That's the red light coming from the amplifier, the transmitter. And then the bottom pictures of the receiver on the other side of the door. And I show multiple images so you can see that the screws, you have to drill them carefully in the correct position so they go through the end of that fiber unit. If you saw in an earlier part of the video that they have holes in them to mount them. And these nuts and bolts came with it. These are really tiny nuts and bolts. I mean, I had a real struggle getting my fat fingers to get these mounted. Also, I'm just showing you this, for your own benefit. If you don't want this little tiny thing that I have, which really would be represented by that 6-inch. Now, the reason I didn't use this 6-inch linear actuator is because the motor sticks out very obviously, whereas the one that I used, it is almost indiscernible in that black plastic housing up at the top. But these all have the same kind of look, but you can get them up to 30 inches. Now it says 220 pounds, 1,000 newtons. I wouldn't go with that. So if you're going to use a bigger garage door, and you want 12 inches, 20 inches, whatever, you still need to use something lightweight, and ABS will do the job. You could even use Luan, quarter-inch plywood. You don't have to use ABS. But I wouldn't advise doing a 30-inch stroke with 3/4-inch plywood, even though you would think, well, that's well under 220 pounds. I have read reviews on these actuators where they didn't quite come up to their rated force, in this case 220 pounds or 1,000 Newton force. I'm also going to post another video that shows some other construction I did with ABS and glue. I built a 2-axis actuator for stepper motors. I'll put that in a subsequent video. Thank you for watching.